Hi everyone. So last time we talked about how to define addition over natural numbers. And our definition is purely based on how we actually carry out counting. And also, of course, based on how natural numbers were defined in the first place. We will continue that discussion next week when we discuss the commutative and associative laws of addition and only over natural numbers for now. Today, we want to switch a little bit to a different topic and very important one, and that's about word problems. So, you have already studied some word problems, but right now, in the fifth grade, this is a critical point, and this is an excellent opportunity at Free Asian Math for us to study or restudy some of the most important or classic word problems. Why this is a critical time to do that? Because next year you will officially start learning algebra. And as some of you may have known, algebra is an extremely powerful tool that can be used to solve many word problems very easily. However, that power comes at a cost. That is that when you use algebra to solve word problems, a lot of the inherent logical relationship that would show itself if you use a arithmetical method to solve the same problem, that type of logical reasoning will get lost when you use algebra to solve the problem. Why? Because a lot of the logics will be actually embodied in the mechanics of solving equations. That's how algebra works. So today we will actually walk you through why we need to study word problems, or if you know some of them already, we will restart them, but kind of systematically. And there's a rule at Free Asian Math, fifth grade, that is that whenever you have a word problem, you are prohibited from using any algebra method to solve the problem, even if you have already learned some algebra. You are only allowed to use arithmetical methods. And the reason is we want to really train you to be smarter. Let's face it, when you use algebra, when you are really good at using algebra to solve word problems, you will become smarter. But if you learn arithmetical methods before learning algebra, then you will become much smarter. Trust me. All right, so let's first review why we want to study word problems. So why did we want to study math in the first place? Math itself, as we mentioned at the very beginning of this class, is abstract in nature. However, we really want to use math as an abstract tool to solve real world problems. And that's exactly why we want to study how to solve word problems, because those word problems really kind of, they're kind of just artificially written problem for you, but they mimic real world problems. In fact, any real world problem can be considered a word problem because you can only describe your problem in words, right? So, studying word problem has two significant meanings. First, you will learn how to read the information inside each problem. And that's very close to any future problem, whether they are mathematical problem or some other type of problem. You can only describe a problem in words, whether it's in English or another language like Chinese or Russian or French, whatever language you use, you describe the problem in words. So it's very important to understand what the statements about the problem they are. So that's the first goal, how to read the information. And then the second very important benefit of learning how to solve word problems is that you will learn how to perform logical reasoning. All those statements, all those conditions, constraints in the problem give you a variety of relationships. And based on such relationships, you can perform logical reasoning. So that's essentially what you will do to solve any problems. But on the other hand, word problem with arithmetic methods kind of difficult because you don't perform logical reasoning along a well-defined linear path. By that, there's no fixed formula for you to follow how to perform logical reasoning. Actually, when you learn how to use algebra later, there's kind of very systematic approach. And that is that roughly when you try to use algebra to solve a word problem, essentially all you need to do is to read the English statements very carefully and translate each relevant English statement into a corresponding mathematical statement. And that mathematical statement usually will give you some equations. That's the essence of using algebra to solve word problem. And it's a very learnable skill, and it's very mechanical once you recognize how to do it. On the other hand, word problem, if you don't have the great tool of algebra, then you have to do some ad hoc reasoning to figure out a particular pattern inside the problem. Sometimes the pattern could be kind of complex, could be a combination of multiple sub-patterns, and you have to identify those patterns, understand the inherent relationships, then apply your skills. That's exactly why you can learn a lot of logical reasoning. Okay? It's a great opportunity to train you to become a much smarter student. Okay, so that's re-emphasize that we really want to train you to learn arithmetical methods first before you learn algebra. Once again, we already discussed the strengths or the benefit of arithmetical method, but the mirror image is that since algebra is so powerful, what is the weakness of algebra? Well, it's exactly the opposite of arithmetical methods. When you use algebra to solve a problem, usually you just follow what I just described, finding the mathematical statement and then finding the relationship, write down the equations, solve the equations. In that process, a lot of the particular features of a given problem are actually hidden inside the very mechanical process of solving an equation or a system of equations. Usually, when you solve equations, you don't care about the underlying physical meanings of those equations. Once the equations are written, you just solve them through a very, very mechanical process. And that kind of wipes out all the inherent logical reasoning feature of the word problem. So, in other words, if you only know how to use algebra, you cannot actually understand the problem at a deeper level. So much promotion of the mathematical, arithmetical methods. So let's look at a few very specific mechanics about arithmetical methods. Usually, when you have a word problem, any problem of reasonable complexity, a very common and very important just kind of a trick is that very often you need to identify a multiplicative relationship. Any reasonably complex word problem involves some multiplicative relationships. For example, the very common speed-based problem. When you have any kind of speed-based problem, essentially you have three variables or three quantities. One is distance, one is the speed, one is the time you need to perform whatever travel method, driving, flying, whatever. So what is the distance? It's just the distance you travel from point A to point B. And what is speed? Speed is the amount of distance you traveled over a unit time, whether it's an hour, minute, or whatever unit you want to choose. So it's kind of distance over time. And that relationship is defined as speed. So of course, the third variable is just the time you need for the travel, whether it's driving or flying, doesn't matter. So you can clearly see there's a relationship, the speed, because it's defined distance over time, then it times time will give you the distance. So that's the multiplicative relationship among those three variables. And there are many, many similar examples, but of all kinds of just real world situations. For example, if you are 16 years old, you are legally allowed to say have a summer job, a part-time job, say at Burger King or McDonald's. Yes, it's not a very kind of really fun job like flipping the burgers or maybe working as a cashier, but you can earn some real money, right? So what is the way to figure out how much money you can earn over, say, 2 weeks or 2 days? Usually you are being paid by hours. So your wage over, say, a 2 days period will be defined by two quantities. One is what's your earning per hour, or hourly wage. Usually that's the state, each state is different. Usually that's around the state minimum wage legally set at a certain number, say $10 an hour, something like that, or $9.5 an hour. That's your hourly wage. And what is the hourly wage? It's the amount of money you can earn over a single hour. And then another quantity is that how many hours you worked. So your total wage over that amount of time would be your hourly wage times the total hours you worked. So that's another example. If you think about it, despite their apparent difference, the logical relationship like this one is almost exactly like the speed example, right? The distance is the speed times time, where here total wage is your hourly wage times the hours you worked. Another example is a lot of you have already learned how to calculate the area of a rectangle. Well, if you have rectangle, a rectangle is defined by two quantities. One is the length, one is the width of the rectangle. And the area of that rectangle is actually defined as the product of those two quantities. So here, this example is a little bit different from the previous two in the sense that the relationship between the length and the width, it's kind of, they're on equal footing, except one is length, one is width, but they're kind of just parallel to each other or symmetrical about each other. But regardless, this is still a multiplicative relationship because the area is the multiplication of those two quantities. Okay, so in real life, we have a lot of those relationships. And in many word problems, you need to identify one or even more than one such relationships, and understanding their just kinds of just complex situations to identify them, it's a key skill to solve many word problems. Okay. So, because we know in multiplication you have three quantities, and there's a multiplication right there, then you actually can get two divisions based on one single multiplication. This is because a division is actually just another name for the multiplication. Or to be mathematically accurate, we call that the inverse of a multiplication. So we can illustrate by examples. In the earlier distance, the speed example, distance equals speed times time, right? So because of that multiplication, we can get two, not just one, inverse in division. So because of that relationship, we can know the speed is actually distance divided by time. And on the other hand, time is distance divided by speed. Essentially, those two relationships are just restatement of the earlier multiplicative relationship. We just restate that relationship in a different way. In those two cases, we represent the same relationship as two division problem, but essentially the three are all the same relationship. So this is also very important to recognize because, say, for example, in one problem, you're only given the distance and the time, then you will know you can get a third one by deploying division rather than multiplication. You can get a speed by performing a division operation. So, but they are all essentially the same. So it's very important to recognize first, you need to identify such a multiplicative relationship and also keenly understand that sometimes this multiplicative relationship is actually just kind of given to you in the division manner. All right. So there's another kind of often underemphasized just principle for you to do. For any non-trivial word problems, you usually when you do the analysis, you will take multiple steps. Okay. But it will be a great skill. This will only come from practice and experience. If you can somehow combine those multiple steps into one single step, and because it's a single step, it will be some mixed operations. Essentially, you will just merge them into one step. Of course, you usually cannot do that without performing some real multi-step analysis first. And at the very beginning, you may only be able to write down such a single step mix operation after you actually perform the multi-step operations. But that's okay. Gradually, you may kind of take a shortcut for simpler ones at least. You can write down the single step mixed operation directly, at least kind of artificially. And we will work through a problem to illustrate what we mean. So look at this problem. We have two guys, Alex and Bill. We were told that the average age of those two guys is 35. Okay, that's our first statement. Hold on to that. The next statement is that the average age of now Alex, Bill, and Carl. So we have a third guy now, Carl. The average age of those three people is 46. So now the question is that how old is Carl? This is a very common word problem. So we want to see how we can get Carl, right? So you have to first examine each statement carefully to see what kind of a relationship you can find. How can we find out the Carl? Because the first statement does not even involve Carl, so certainly we cannot do anything about it. The only information available about Carl is the second statement, and that is that the average age of the three guys, Alex, Bill, and Carl, is 46. And this is similar to the first statement anyway, but this one does give us information about Carl. So what typically does this statement do? you should recognize what is the average age means. Well, average means that you add them up, then divided by total number of people. All right? So that truly gives you some motivation, say, this average will involve some division, and that is the division of the total age of the three guys, and that gives me a relationship. However, when you do the division, it kind of just you lose some information about the age, the direct information that was given to you, the age of the three guys. So how you can overcome that? So you think about if the average is 46 of the three guys, now how can I translate this statement into an easier to work or more helpful kind of relationship? You would multiply that by 3, right? Because this is just reversed process of averaging. Averaging is you first add those 3 up, then divide it by 3. But if I multiply this average by 3, I will restore the total age of the 3 guys. Is that cool? So this is a very important step of the analysis. So if we multiply 46 by 3, which gives you 138, usually there's one more catch, which we will emphasize shortly. When you do multi-steps, you usually want to specify the unit of your result at each step. In this case, you can write down things like years, or this is just a kind of reminder for yourself. Don't lose track of the physical meaning of what you are doing, what you are getting right now. So I would just say, write this as a year. I write a Y to represent this 138 means the total age of the 3 guys. So I will know this is only in my mind. This really means that I have Alex's age plus Bill's age plus Carl's age. Of course, you don't need to write this down on paper, but this is something in my mind. Okay, so if we can do this for the 3 guys, we can certainly do this for the first 2 guys. That is, the average of Alex and Bill is 35. So now this time I just multiply that number by 2. 35 times 2 equals 70 years. Now I kind of transform both statements into an easier format. Information is more direct. So the first one now is the age of the 3 guys, and the second number 70 is the total age of 2 guys. Then what is the relationship between the two? Now it's quite obvious. If I subtract the second number 70 from the first one, 138 minus 70, this must be the 3rd guy's age, because the first number is the total age of 3 guys, A, B, C, and the second is just A, B. So subtracting second from the first must be the age of that 3rd guy, which is Carl's age. So this gives me an easy number, 68. Now I know this is exactly Carl's age. And that's what being asked for. How old is Carl? So done. So what we just went through is a so-called multi-step just procedure to get this down, right? This is perfectly fine. But you can see that it's a little bit slow. And there's one more issue other than the time and the resources you spend. When you look at those 3 steps, you cannot immediately tell the relationship. Yes, there is a relationship 138 right here. This is 138, 170, and they are both used in this 3rd step. We subtract the second from the first, but because they're scattered within 3 different steps, it's not very visually at this. It's not very easy to see this relationship right away. What you can do, if we combine those 3 steps into one step, then that relationship kind of being promoted more, kind of more obvious, or you push that to be more obvious. But how do we do that? Well, now you will use something called mix operation. Essentially, you have more than one steps, but you force them to be mixed with each other. But however, we want to exhibit a certain order among those steps. So we will have to use both what we call the order of operations when that can help, or sometimes we are forced to use something called parentheses to force certain order. If you have not learned the order of operations or the meaning of parentheses, don't worry. This at this time we don't assume you know, but we will pick it up on the fly, and later we'll formally discuss when we discuss arithmetic operations. So in this case, you see that this relationship 138 minus 70 came at last, right? So that means that we have performed the first 2 steps to get 138 and 70. So if we want to write all the 3 into 1, that will be 46 times 3, because we want to do this first, and 35 times 2, we want to do that also before the subtraction. Then we combine those 2 by subtraction. And this is indeed what we would call a single step mix operation, because you write everything in just one step. Okay, if you do understand the order of operations, you would recognize that because we have 2 multiplications, they are both more advanced than the subtraction, which is of the same precedence as addition. So in this time, the actual parentheses are not necessary. We can write this down, the same thing. But at this time, because we want to emphasize this single step logical relationship, we want to add those parentheses even they are not necessary. So this is how we would call a single step operation. It's very important for you to see that in this step, you kind of illustrated the logical relationship, the flow of the logic more clearly. We want to do those multiplication and then subtract the second one from the first one. So when you write down this, when you actually resolve it, and this is how you should do in your homework, you should write down something like this. Also, you don't have to, if you perform the multi-step, you don't have to redo the single step mix operation. But if you are a student really aspiring to be excellent, I highly suggest you do the same thing. So this is essentially repetition of what you would do in the earlier multi-step operation. So 46 times 3 will be written as 138 minus 35 times 2, that's 30, and you get 68. And usually you still want to add something like years or just y, just for yourself to make sure that you are tracking what exactly you are trying to do here. Okay, so this will be a perfect solution for your problem. So either the multi-step procedure will work well, or if you can write that into a single mixed step, this will work even better. So as you can see, you can save just a little bit time when you do single step operation, because for example, you can write those down 138, 70, those 2 steps in just one shot. In a single step, you can perform 2 at once, then do the subtraction. In contrast, if you go back to multi-step, you can see that here you do 138, then you have to copy down 138. So that's a little bit saving of your time. But most importantly, this is logically more clear. the flow is much easier to follow. Okay, so those details are important for you as part of your training to make sure that when you do your homework, follow detailed steps like this. It's an absolute horrible thing in American education that your school math teachers do not require you to write down the detailed steps. And it's even worse when you do math, just exams or competitions, you just need to write down the final result without performing those detailed steps. At least at this young age, as part of your mathematical training, you are mandated to do things like this. At least here at Free Asian Math, in your homework, and every time you have the opportunities, write down the steps and clearly demonstrate to yourself what you are doing. Don't forget, as intermediate step, write down some just kind of the unit every step of the way, and we will show how to do that. Okay, so this is just an illustration. You want to sometimes you want to really challenge yourself. Can I do this in just one step with mixed operation? But of course, to be able to do that, you have to first understand the order of operations. If you don't understand that yet, it's okay. Use parentheses to help you. What the parentheses does is that whenever something goes inside the parentheses, that operation will be always computed first over other things, unless you have parentheses inside the parentheses. Okay, you will gradually get a better idea of what I'm talking about. So at this time, if you are a little bit confused, don't worry. All right. So let's talk about some very basic and very important classic word problem just today. And we will re-emphasize that you want to add the unit into your multi-step operations. Every step, you want to track down the physical meaning of the result. What I'm getting is 35, 68. What does it mean? Without the unit, that number is nothing. And it's very good way to prevent mistakes, because when the units don't match, your arithmetical operation is meaningless. You cannot add apples to bananas. Okay? For example, you cannot time your speed, your driving speed, to how many hours you worked. That's irrelevant. You have to times driving speed to the hours you drove, not the hours you worked. Otherwise, the two, even they are the same hours, the unit is the same, but they have very different context. You just cannot do that. What do we get if you times say, I drive 60 hours per hour and I work 5 hours this morning? You multiply it together, what do we get? You get absolutely nonsense. Okay, so let's talk about a very simple but very important and kind of building block type of classic word problem, what we call a unit first problem. Let's look at an example, all right? So this problem 5.5.1.1, Aaron is reading a book of 385 pages at a steady pace, meaning that he will read the same number of pages every day. So he read 105 pages in the first 3 days. How many days in total does Aaron need to finish reading the book? Okay, so first you want to focus on what the question is about. The question is that how many days in total does the Aaron need to finish reading the book? What do you have? You already know the total number of pages, right? You know the book is 385 pages. And now you are asked to tell how many days in total does Aaron need to finish reading the book? How should we start? Well, you can reason backwards. If I do know how many days in total, let's just say 3 days, 5 days, whatever that day numbers is, then what actually you get? Well, you already know, say the total is 385. Perhaps when we have problem like this, we want to move this window a little bit closer so that you remember. Hopefully you can still read this, not too small. So if you do know the total number of pages, 385, you ask how many days you needed. Let's just presume that you know the answer how many days. Let's just say 5 days. Then what will you actually get? You will be able to calculate the actual pace of your reading if you actually just spend 5 days, right? The total number of pages of book, the days that you spend on the book, that will give you the pace. In this case, 185 divided by 5, you will get 7. You will get the remainder would be 35, 3. You get 7 again. What is the unit of this quantity? This is hypothetical for now, okay? We just assume this is 5. You will get, on average, how many pages you will read a day, right? So we will just write this as page per day, okay? So this is just shorthand notation, say for this one, how many pages we will be able to, Aaron will be able to read. So the unit is page per day. But remember, this unit usually is kind of a reminder for yourself, tracking down what I'm working on. So you don't have to write down that fully. You can use some just shorthanded notation like this, okay? But this is not what was given in the problem. It just gives you the idea what you will get. You will get a reading pace. However, if you go back to the problem, you'll see that a similar quantity has already been provided to you because the problem already told you that Aaron read 105 pages in 3 days. What does that statement give you? It gives you the actual number, but same concept. That gives you a pace. So if you divide that 100, sorry, I should not use a fraction notation here. I apologize because I forgot that you guys have not officially studied fraction, but some of you, I know you did, but I do not assume anything. I believe because some of you guys are actually in 4th grade. I'm not sure. If you are in 5th grade, you should have already learned fraction, but we still pretend that you have not really learned fractions because at free Asian math, we will give you a really deep run on fractions this year. So we just use regular division. But the problem already told you that Aaron could read this in 3 days, 155 pages. So this will give you the actual. So the first one is just imaginary, hypothetical, not something real, just give you the concept. But the second one is the real thing. 35 pages per day. Why we are connecting those two, this illustrates the very first important principle we discussed. In a lot of problems, you are trying to find a multiplicative relationship among 3 quantities. Remember, multiplicative relationship can actually be in disguise as a division, and that's exactly what we have here. So 105 pages divided by 3 days give you 35 pages per day. This is a division, but if you do the reverse, if you say 105 is 3 times 35, that's exactly what we talk about. That's a multiplicative relationship. Okay, why this is relevant? Now, because of this, we know the actual pace is just 35. But based on the same relationship, if the total book is 385, and now you need to actually to figure out this guy. Remember, this is just hypothetical. We assume Aaron can finish in 5 days. Now we want to calculate the actual how many days Aaron can finish. Then it's just this 385 divided by the real pace. So if we use 385 divided by the real pace, which is 35 here, we should get back to the days. Remember, here is the number of days. This is also the number of days. Well, this one is the actual. This is the one just for our analysis purpose. We just assume there's actually how many days. But that's what we are trying to exactly figure out right now. And that is based on this number we computed is 35, which is pages per day. So the total number of pages, 385, divided by this page, 35 pages per day, should give us the actual number that Aaron needs to read the book. And that is 11 days. So we write down as 11 days. So what are we doing here? We are trying to find, then reuse a multiplicative relationship. We first identify what reading pace Aaron had, and that was actually indirectly given. You were told that he can read 105 pages in 3 days. That gives you a pace. And we will see shortly, this is exactly why we call this the unit first, because this is a unit quantity. Where does the unit concept come from? It's this per day. This is page per day, right? So that is a unit. A unit is a day, every day. In single day, how many pages Aaron can read. So this is what we call the unit quantity. So you calculate that first. 105 divided by 3, get this. Now we divide the total number of pages by this quantity and get the 11 days we needed. So this second step is nothing but re-recognizing this multiplicative relationship. The first one is a kind of sample, 105 pages. Now in the second one, we use the real total number of pages divided by that pace. So if this is a multi-step, this one is our imaginary, just to illustrate the concept. You need to take those 2 steps to get this answer. Now, how about we want to combine those into a single step mix operation? Apparently, the first one goes first, then we have the second. So what you want to do is write down, I will use blue for this. So 105 divided by 3, because the result of this step will become the divider in the second step. I want to put a parenthesis to make sure that this will give me just a result, a number. And this number will serve as the divider in this second step. So I would just write this as 385 divided by this number. And this number is the result of the first division. This is how we write down the single step mixed operation for this problem. And it's very important to recognize what we just did here. We get the pace and pages per day. That is what we call the unit quantity. Okay, so now let's move on to a second problem. So we spent so much time on the first problem. Hopefully the second problem and the rest of the problem will come easier. Now, a very similar problem. Once again, Aaron is reading a book at a steady pace. He read 105 pages in the first 3 days, exactly as the problem. But what did we know? And now we were told, look, we did not even know, as in the first problem, what the total page, number of pages the book has. But we do know now Aaron needs 18 days to finish reading the book. And now the problem actually is how many pages does the book have? If you have already mastered the first problem, you can see that the second problem is almost the same, except we flip one known to one unknown and flip the unknown to the known. That is, in the first problem, we know the total number of pages. We need to know how many days Aaron needs to need. Aaron is going to need. In the second, that relationship is reversed. This time we know how many days Aaron needs to finish reading the book, but now we don't know the total number of books, right? So this time we will use exactly the same first step. We will get 105 divided by 3. That's the pace. That's the unit quantity we are talking about here. This is how many pages per day. This time, remember, division, multiplication, they are inverse to each other. This time we will just times day, 18 days, because the first quantity gives us how many pages per day, and now we know Aaron spends 18 days. This would give us the total number of the pages. And you can recognize that once you have mastered the first problem, for this second problem, we were able to write down the single step of multiplication. And this will give us 35 times 18. Performing some mental math, we can use some trick that we will learn later. We can convert this in 70 times 9. 7 times 9, that's 63. So the total number of pages of book is 630 pages. Okay, we write P to denote pages. So you can see that this problem is very closely related to the first one, except here, instead of using the total number of pages divided by this unit quantity, we are now multiplying this unit quantity with the total number of days to get total number of pages. But all the underlying relationship is that multiplicative. And what is this multiplicative? This is pages read per day times the number of days on reading will give you the total number of pages. That's the fundamental multiplicative relationship here. And for this class of problem, in this way, we focus on this quantity first. It's a unit quantity. This is the page read per day. Okay, so for both 5.1.1 and 5.1.2, we need to compute this one first. The difference between 1 and 2 is that for the second, we do the multiplication, and for the first, we know this number, we do the division to get the days on reading. But in both cases, we need to compute this one first. Okay, so that's why this type of problems is called unit first. We need to calculate this unit quantity first. Okay, this sounds very mechanical, right? Are we trying to train you to become a robot to memorize things? Absolutely not. But there are some problems that are so fundamental, you just think about them like when you do Lego, there are some fundamental building blocks. You immediately see what their shapes are, what functions they are, what they do. So this is not just to trying to become a robot. This is really building your basic toolbox. Okay, if you recognize this type of problem, you can do more complicated problems, and that comes in in the next one. So this is a more complicated problem, but fundamentally it's still the same concept. Now, we have a team of 4 volunteers. They can package 120 first aid kits in 2 hours. Look, this statement is considerably more difficult or more complex than some of the statements we just saw in the last 2 problems. Now, the question is, if a team of 15 volunteers work for 8 hours, how many first aid kits can they package? Well, both the statement and the second hypothetical becomes considerably more complicated. But you should not be distracted by that information. You should still look for the fundamental concept. What is the fundamental concept here? We have in the statement question, we know the number of volunteers, we know how long they worked. We want to figure out the output of their work. What is the relationship? Well, it's still a multiplicative relationship, but this time the multiplication will become considerably more complicated because it's not just one times the other. There are 3 quantities multiplied altogether to get the product. And what is that? You need to know the number of volunteers and how long each volunteer works, how many hours, but none of them will give you the unit quantity you needed. And what is that unit quantity? That is how many first aid kits can one volunteer package in 1 hour. So in other words, that unit looks like this. How many kids? K. How many people? 1 person. And this unit is not just 1 person, but also times 1 hour. It's a person and hour multiplied together. That's the unit. It's not just 1 single person. How many kids can 1 person package? Because that is quite meaningless because we don't know how long this person will work, how many hours. So to give a meaningful quantity, how many first aid kits can we get? That unit must be in terms of both a person and hour that person works. So that's 1 person, 1 hour. Do we know this unit quantity? Yes, we do, because the very first statement just gave us that information. So we have 4 volunteers. They each work 2 hours to get this 120 kits. So what is the unit? It's 120 divided by 2 divided by 4. You can recognize that it doesn't matter you divide 2 first or dividing 4 first. They are both the same. This will give you 60 divided by 4, that's 15. So you really want to write down this as the number of kids, and this 1 person and 1 hour. Write down something like that. Okay? Once you know this, you will see that the total with 15 volunteers, 8 hours, is simply we multiply this unit quantity, because now you see that that's exactly why you need to write down those units as kind of a reminder what is the physical meaning of this quantity. Now you simply multiply this already calculated unit quantity, which is 15 kids per person per hour, times how many people you have? 15 volunteers. How long they work together? 8 hours. So this will cancel out this person, and A will cancel out hours, and the result will give you the total number of kids. So this is 15 times 15 times 8. This represents the number of people, and this represents the number of hours all those people work together. And this is the unit, that productivity, a unit quantity, 15 kids per person per hour. And this finally will give you 15 times 15, that's 225 times A. You can do some mental math. You divide this, um, break down A into 4 times 2. 4 times 225, that's 900. So this will give you 1800. And don't forget, you want to write down the quantity, the unit as kids. So the answer is that 15 volunteers in 8 hours, they can package 1,800 kids, first aid kits. So if you want to write down the 2 steps into one single mix operation, what will you do? Well, almost just what we did earlier. We combine those 2 steps into one. This is the first one, give you the unit quantity, then you times this by 15 times 8. Look at this. This actually gives you a very clear logical flow. You divide the first kind of a sample, divided by the hours, divided by number of people, then you multiply the same quantity back, then times the new number of people, the new number of hours, get the new total. Get this would be, you do something really quick, and you can write, wait, then you just do this in one step, depending on how good you are at basic multiplication. You can write down this in one step or 2 steps. So in this case, I already know it's 1800. I just write down this as 1800 kids. That's how you would do. So you consider this problem, it's fundamentally the same as the first 2 problems, except that in order to get the unit quantity, instead of just do one more division, now you have to divide this total by 2 quantities, both the people, the number of people, and number of hours. So both problems are the same unit first problem. Okay, so we don't have much time left, but we will extend a little bit. Maybe we will go 5 or 10 minutes over. Sometimes this happens, so stay with me. If you have to leave earlier, you can always watch the video playback. All right, so that's what we call the unit first problems. Okay, the key concept in those type problem is that you identify certain multiplicative relationship and recognize a so-called unit quantity. All right, and that will be the stepping stone toward computing the required quantity, whatever that is. And in the last step, you can use the unit quantity either in the multiplication or in the division relationship. But the key is that calculate that unit quantity first. Now we look at a closely related problem, and we will skip this question because we are running out of time. A very similar one. You can read the handout. We'll skip this problem. So we will go to a closely related concept, another class of problem. Now this time we call that total first, and we'll see what that means. Now our friend Aaron, once again, Aaron read a book at a steady pace of 35 pages a day. Now you can see this is very different from the first couple of problems, especially the Aaron reading problem. Now, what are we getting right now? We are already told what the reading pace is. It's 35 pages a day. In other words, what we say total first, that quantity is already given to us. Okay? Now, he didn't finish the book in 8 days. Now, Aaron's younger brother Albert is actually a faster reader, and he can read the same book at a pace of 40 pages a day. Sometimes faster does not necessarily mean better, right? If you understand that, what is the goodness of being faster if you comprehend less materials? But assume that's not the case. So Albert is simply a faster reader. So he can read the same book at a pace of 40 pages. Now, how many days does Albert need to finish reading the book? From exactly same relationship, your pace of reading times the number of how many days you spend will give you the total number of the page that you actually read. Maybe you finish the whole book, that's still the total number of pages you read. If we want to answer this question, how many days does Albert need to finish reading the book? From the same multiplicative relationship, what do we need to know? We need to know two things. Albert's reading pace, which is already given to us, is 40 pages a day. Then the other quantity we need to know is the total number of pages of the book, right? Remember, in the first couple of problems, that quantity was actually given to us. In other words, we already knew the total earlier. We did not know the unit quantity, which is the pace. In this case, Albert's pace is given. We need to figure out how many days. Now we need to know the total number that Albert needs to finish. And that is the total number of pages of the book. How do we know that? Well, we can actually get that from Aaron's reading situation. We were told that Aaron can read this book at 35 pages a day, and with 8 days, that's exactly the same multiplicative relationship. So in this case, we can easily tell the total number of pages of book is 35 times 8. That is 280 pages. Why? The same multiplicative relationship. 35 pages a day, 8 days, so the total is 280 pages. We got this from Aaron. Now, apply the same number of pages to Albert's reading situation. Albert is a fast reader, so he needs 280 divided by 40. That's his pace, 40 pages per day. Then we get 7 days. To see why this is the unit is day, remember the quantity is unit. This is a page. And what is 40? 40 is pages per day. So you haven't learned fraction yet, but think about this. When you divide this, it's essentially flip the D to the top. So you don't have to understand this completely, but you should understand the physical meaning. When you have total number of pages divided by pages per day, you get the quantity of day. Okay, so that's why Albert now only needs 7 days. It's very important to recognize that in this type of problem, we knew the pace actually for both Aaron and Albert, but we need to calculate this first. This is not very surprising. We call this the total first. We calculated the total number of pages of a book first. And that's why this type of problem is called total first. It's very closely related. It's just within the same multiplicative relationship, which is given to you, which is not. So from what is given to you, you calculate the unknown yet. So depending on which unknown is that, sometimes it's the unit quantity is unknown. You need to do that first, and that's called unit first. Sometimes it's the total unknown. You calculate the total first, and that is called total first. That's why the two types of problems are very closely related. And if we need to do single step operation, mixed operation, what would this be? It's just 35 times A, that gives you the total, then divided by Albert's pace, and this is what you should write down for the single step mix operation for this problem. Okay, so that's the total first problem. So we will just quickly run through one more example, a very similar one, except this one just add a little bit twist. So we have a construction company. This company, let's just say, when a government contract to build a highway. So the company plans to build this highway with 500 workers and in 240 days. Okay? So now some weather conditions just got changed, some unexpected weather conditions. Now the project must be finished instead of 240 days, must be finished in just 200 days, meaning that 40 days less. Of course, you have to do it quicker, so you have to put in more worker so that the labor will be more, so you can do it faster. So with the total projected manpower unchanged, meaning that you just need to shorten the time, but the total amount of work remains the same. So the manpower needed, the total manpower needed is still same. Now, how many additional workers must the company put into the project now? So forget about the second part of the question, how many additional, because additional is just the new total work subtracting the earlier projected number of workers. So this is essentially the same, just compute how many workers in total you need in this situation. And that is not difficult to see because we still see the multiplicative relationship. What is total amount of work, the work manpower or work hours, is the number of workers times how many days. And that total is person times day. So we can see that because it said that the total manpower unchanged, we need to first calculate what is that total manpower needed. It's 500 times 240, right? So this is, if we write multiple steps, this will give you 22,000. What is this unit? This is man times day. Man times day. Or man day. So that's the total amount of work. Now the new schedule is that you only have 200 days to finish this project. How many workers you need? Of course, we will just divide this 12,000 by the new number of days, 200. Now you get 600 workers. We say 600 men. Okay, but this is not what the problem asks you for. You ask to know how many actual or additional workers you need. But that is straightforward. You subtract 500 from 600, you get 100 men. Okay. For those of you who are politically sensitive, I'm sorry, I should write this MSW as workers, right? I didn't mean that you cannot have a female worker, but it just kind of bad on my part. It doesn't really matter that much though. So I'm trying to be politically correct. Okay, so if you write down this into a single step, what do you need? You just combine all those together, right? You just write down 600 minus parentheses 12,000 divided by 500. Oh no, sorry. I should write that, not write down that. 500 times 240 divided by 200. That is what you will write down. Okay. Also, at this time, we add a lot of parentheses and later, oh, sorry, I'm totally messed this up. It's the other way around. So sometimes I rush myself and get it wrong. Okay. So this would be 500 times, oh, there's one more closing parenthesis. So 500 times 240 divided by 200 and subtracting 500. That's the single step mixed operation. So once again, you can see the big deal here is that you just want to calculate this total quantity first. Okay? So nothing really that impressive in those two types of problem. Unit first, total first, but very important building blocks for you to work on more complicated word problem. And that is what we have started today. So next week, we will switch back to our studying of natural numbers and their uh, arithmetical operations. And from time to time, once in a while, we will add more word problems. So the goal is to finish about 18 types of classical word problems this semester before the Christmas break. That's a lot. So today we just started two of them. I will see you next week. Thank you. Bye bye.